Hey you guys, this is Mr. Sal. We're going to have a quick lesson on angles associated with parallel lines. So I may show some of the answers on some of those. If you need to pause it, do it. Thanks for watching. Don't forget to like, comment, and subscribe. So the first thing we need to do when using a protractor is just understand the parts of it. So, this isn't exact, but something like this, okay? So some of you guys have a protractor and it's got a little hole right there. We need to acknowledge where that hole is because that's an important part of where we need to line these up, okay? Some of you guys don't have one, and at the bottom you may have something that looks like this, okay? The main part of that one is where that, I guess it's kind of like an upside down T right there. It's where that red mark is right there. That would be the same as the pinhole on this one right here. Others of you have one maybe that kind of has a triangle or a diamond right there. The pinhole or this point in red would be the same as this point here in purple. And we need these three because that's going to help us to create a 45-degree angle in this case. So we're just looking at creating some kind of 45-degree angle. Now there's more to it. There's something else we need to look at, and if you got the pinhole, you should have some kind of line like this. If it's got that upside down T, then it's this green line. If you don't have either of those, usually on the metal ones, then we're looking at just the base of the protractor right here. Now, other than that, of course, there's the markings for the angles all around this thing, which we need to acknowledge. But there's two parts. Either it's going to start with 0 here and move this way in the negative direction, or it's going to start with 0 here and move this way in the positive direction. No, I think I had those backwards. This is the positive direction. That's the negative direction. There we go. Now it just depends on where you start. Because if we look at a line, and it doesn't matter what line we look at, it just needs to be a line of some sort, like this one. When we set up the protractor on top of it, so let's say I had the pinhole one, okay? So I need the pinhole to be on a point that I can put on the line. It doesn't matter where it is. Let's say it's right there. So the pinhole would be right on that point. And then the line across it needs to be on the line that I'm trying to create the angle with, okay? So the red line would be on the protractor, the black line is underneath it to create the angle. Now if I'm looking for 45 degrees, there's two 45 degrees. There should be one around here and one around this point as well. So what I would do at the end of that protractor is make a point where it says or shows 45 degrees. Let's use this one. After that, I would use the straight edge of the protractor to create a straight line between those two, like this. Now what we have is a 45-degree angle right here. Now how do I know it's not this one? Because that's an obtuse angle, the green one is. And an obtuse angle is more than 90 degrees, which you guys learned in 7th grade. 45 degrees is acute because it's less than 90 degrees. So automatically I know that that has to be the 45-degree angle. If I had used the other 45-degree angle mark around here, then I would have done the same thing. I would have created a line through those 2 points, but now the 45-degree angle would have been right here. And I don't care which one you used, as long as you created some kind of 45-degree angle. It's this one in green or this one in red. Now mine isn't exact because I don't actually have a protractor on here. But that's how you use the protractor to create angles. So this slide, it's not on the worksheet, but it's going to cover some important vocabulary for you guys. In the picture below, given line L and line M are cut by a transversal line called T. A transversal line is just some line that goes through two or more other lines, but it can't go through the two other lines at the same point. So define transversals in your own words. Draw another transversal for the two lines above and label it line R, which we will do, but let's define this. Alright, so a transversal has to go through two other lines. That's what intersects mean. It has to go through them. So on this diagram, if I made a new diagram of this, like, not that, but this line, and we'll say this line. In fact, I'll take that back and we'll do this. So these two lines, if I wanted a transversal, it can't go through where those two lines intersect. Okay? So, but any other line would work, like on the diagram we have. If I wanted to draw a transversal, I could say this line and label it R, and that is a transversal that goes through lines L and M. That is a transversal now with lines L and M. Now the good news is, as we draw transversals through other lines, it creates relationships between the lines, which we will talk about as we go through this lesson. But it's important for you guys to know what a transversal line is, first of all. Okay. More vocabulary. If I were to look at two lines, let's say this line and this one, we'll call this line L and this line M, because it doesn't matter. And I had a transversal that cut through them, like this one. And we will call that line T for transversal. Okay? Now line T is not intersecting these two lines in the same spot, so we know it's a transversal, and that's good. But this creates angle relationships. The first relationship we need to understand, because we're going to expand on it, is interior and exterior angles. Exterior would be on the outside. So if I'm looking at the two black lines here, the outside would be anything in this area. So this would be considered the exterior. But also above line L in this area would also be considered exterior. Now if it's not exterior, it would be on the inside, which is also known as interior. So we'll have exterior angles and interior angles, which create relationships. But also, and this one you guys should have learned in 7th grade, another type of angle relationship, again you should have learned this in 7th grade, is these types. Does anyone remember how we would classify those two purple angles? Alright, in 7th grade you guys learned that the intersection point is called a vertice. And these angles are through the vertice, and so we would call these vertical. I may have spelled that wrong. Sorry. That's why I teach math and not English. These are vertical. Some people say that it tickles the vertice. Okay, that's kind of weird, but whatever. All right. But these are vertical, one with another. Okay. Another relationship you guys learned in 7th grade, which we will need to acknowledge on this, is if I looked at this angle right here and this angle here as well. Yes, one is obtuse, one is acute in this case. However, these two angles combine to give us this straight line, which kind of rhymes. But how many degrees are in a straight line? 180 degrees. So the green and the blue angle there give us 180 degrees, but we would call that a straight angle relationship. Now straight angles are usually always at the same intersection between two lines, which won't always be the case for us. And we'll discuss that later. Alright, but as long as we have these, at least to build on, then this isn't actually completely new like I had mentioned, alright? Well, that takes us to the first page then in the worksheet, and we'll look at some of the terminology for this as well. In the figure, line 1 is not parallel to line 2, and M is a transversal. Use a protractor to measure angles 1 through 8, which, if any, are equal in measure. Explain why, and you can use a transparency if you need to, which means we may be looking at transformations, all right? So take a moment with your partner, use the protractors that you have, and measure all 8 angles, and then figure out which angles are equivalent. Measure, and I can see from the top here that angle 1 is equal to angle 3, and also angle 4 is equal to angle 2. Then down here at the bottom, angle 5 is equal to angle 7. And then also angle 6 is equal to angle 8. From 7th grade, we got 4 sets of vertical angles, which are all 4 of these, and they're all equal. That's something you guys learned in 7th grade. Vertical angles are always equal. There is something else about this though, is we need to notice on this that angles 1, 2, 3, and 4, even though they correspond with angles 5, 6, 7, and 8, are not equivalent to each other, all right? And there's a reason for that. We'll talk about that in the next problem. In this figure, line 1, which is this line, is parallel to line 2, which is this one. And M is this transversal. Use a protractor to measure angles 1 through 8. List the angles that are equal in the measure. So 2 things. Measure all 8 angles and then figure out which angles are equivalent to each other. Take a moment to do that with your partner. Again, you should have gotten these using your protractor. Before we continue though, let's just list all the angles that are equal in measure. For example, angle 1 is also equal to angle 3. That's these 2 angles. But also, it's equal to this angle, angle 5, which is also equal to angle 7. On the other hand, we've got this obtuse angle, 141, which is angle 2. This is also equal to angle 4, which is also equal to angle 6, which is also equal to this angle, angle 8. Now this is a different set though. This one we have 4 angles that are the same for both sets instead of just 4 sets of 2 angles. Why does this one have lots of angles that are equal, whereas the other one did not? Once we get these 2 lines that are parallel, it makes all the difference. Then we have interesting relationships between these angles, which makes them equivalent, as long as the lines are parallel. So they have to be parallel lines first. So what did you notice about angles 1 and 5? Angle 1, this was 39 degrees. And angle 5, this is also 39 degrees. So they're the same. The question is, though, why? Why do we think that they are the same?
Because they're vertical.
Now, it has to do with the parallel lines, but also we could take this, and if I took that angle, and all I did was translate it down here, then I used a rigid motion to duplicate the angle. Rigid motions do not change sizes of angles. And since it is a rigid motion, then it creates 2 angles that are equivalent. Now that's in addition to the lines being parallel though. What did you notice about the measures of angle 3, which is this angle, and angle 7? both of these were 39 degrees. Well, they're the same. So these angles are the same. Why is that the case? Because once again, if I were to take angle 3 and just trace it on a scratch piece of paper, then I can take this and move it down here, and it's duplicated again. Again, that's just a translation, and translations will keep angles the same. So this is good news because we've done translations before, so this isn't completely new stuff for us. Are there any other pairs of angles with the same relationship? If so, list them. Yes, there is. We just identified one of them before. I think it was angle 1 and angle 5. But also angles 2, use a different color. Angles 2 and 6, and also 4 and 8. These have the same relationship. The relationship between these angles is corresponding angles. Corresponding angles are angles in the same location of different intersections. So again, we're looking at two lines with the transversal, and the two lines don't have to be parallel. However, so let's look at these two intersections. There's one vertex and there's the other vertex. This angle would be corresponding with this angle because it's in the same position of different intersections. Now, as soon as the lines are parallel, so if we got rid of one of these and we made it a parallel line, something like this, then these two blue angles would become equivalent, just like we saw in that last example. So listing that set of angles, we kind of did that already. 4 and 8 have the same relationship, and so do 2 and 6 on that. Part C, what did you notice about the measures of angle 4 and 6? So this angle 4, that was 141 degrees. And angle 6, which was also 141 degrees. Well, these are the same measure. Why do we think this is the case? It's because I can take this angle, that looks a little better, and if I took that red angle and I translated it here, I could also rotate it. Yeah, so you could reflect it. I'm going to rotate it, and then I get the same angle right here. And rotations are also rigid motions, so they're going to keep the angles the same. Is there any other pairs of angles with the same relationship? Yeah, sure there is. One that I notice is 3 and 5. This would have that relationship of making a translation and then also a rotation to create that angle. So this brings up another angle relationship. Let's look at this with parallel lines and a transversal like this one. If I look at this purple angle and this purple angle, they are equivalent when the lines are parallel. They're on the interior, but they're alternating, which is why we call these alternating or alternate interior angles. But of course there is another set on this diagram. It would be this green set. That angle and this angle also would be alternate interior angles. They're on the interior, but they're on opposite sides of the transversal at different intersections. So this problem set, identify all pairs of corresponding angles. Well, looks like we've got 1 and 5, and 2 and 6, and 3 and 7 correspond, and then 4 and 8 also correspond. So this is kind of color-coded. Are these pairs of corresponding angles equal? No, we cannot say that these are because we don't know if line 1 is parallel to line 2. Identify all pairs of alternate interior angles. We just covered that. That would be angle 4 and angle 5. And also angle 3 is alternate interior with angle 6. Are these equal in measure? No, they are not, because it didn't say anything about line 1 being parallel to line 2, which is what it says on this next slide. Use an informal argument to describe why angle 1 and angle 8 are equal in measure if line 1 is parallel to line 2. So that's angle 1 and also angle 8. Well, we haven't seen this yet, but if I were to take angle 1 and just trace it on a scratch piece of paper, I can move this line down, which gives me line 5, and then I can just rotate this to get line 8. So here we go, rotation and line 8. So I use two rigid motions to get angle 8 from line 1, or from angle 1, which means that these two are equivalent. Now again, that's only because the two lines are parallel that we could say that. Alright, this brings up a new relationship which we need to talk about. Alternate exterior angles. Assuming these two lines are parallel, line 1 and line 2, if the measure of angle 4, we'll write that in, angle 4, if this is 73 degrees, what is the measure of angle 8, which is right here? And how do we know? Well, angle 8 is corresponding with angle 4, so it also would be 73 degrees, because line 2 and line 1 are parallel. If they weren't parallel, we wouldn't be able to know what angle 8 is from angle 4. Number 5, assuming these two lines are parallel, if the measure of angle 3 is 107 degrees, so we'll label that 107 degrees. What is the measure of angle 6, which is this angle? Does anyone know the relationship between these two angles, 3 and 6? Well, the relationship though. So these aren't going to be the same only because these are parallel. But the relationship between these, they're interior and they're alternating. So this is alternate exterior and interior angles, rather. So this also would be 107 degrees. Assuming line 1 is parallel to line 2, if the measure of angle 2 is 107 degrees, which is this angle, then what is the measure of angle 7? This one also would be 107 degrees because these are alternate exterior angles, and when lines are parallel, alternate exterior angles are the same. Would your answers to problem 4 through 6 be the same if you had not been informed that line 1 is parallel to line 2? Why or why not? Well, the answer is no, they would not have been the same, because once lines are not parallel, those relationships that we talked about, corresponding angles, alternate interior angles, and alternate exterior angles, they would not be equal if the lines are not parallel. Use an informal argument to describe why angle 1 and angle 5 are equal in measure if line 1 is parallel to line 2. Well, this is angle 1, and this is angle 5. These are corresponding angles because they're in the same position of different intersections. And the two lines are parallel, so corresponding angles would be equivalent. Now in this description they use the translation, which you could have done as well. Angle 1 is just translated down into angle 5. Use an informal argument to describe why angle 4 and angle 5 are equal in measure if line 1 is parallel to line 2. So angle 4 compared to angle 5. Again, these are alternate interior angles because they're sandwiched between the two parallel lines. However, again, you could have used a translation and then a rotation to map 4 onto angle 5. Assume that line 1 is not parallel to line 2. Explain why angle 3 is not equal to angle 7.